From the last video, we looked at the unit step function and the delta function, and then we looked at some circuit analysis for RC circuits and RLC circuits, and we set up the differential equations that we would have to solve. Now, depending on the input voltage or other parameters, those differential equations can become awful. So we seek to find a way to make those differential equations easier to work with. And our answer to that is using the Laplace transform. So the Laplace transform takes us from the time domain in t to the complex frequency domain s, which is represented as sigma plus j omega. And we're going to work with a unilateral Laplace transform, where we can transform a function given in time into the complex frequency by this integral 0 from the left all the way to infinity, f of t times e to the minus st with respect to t. And sometimes we replace this 0 from the left with just a normal 0. So sometimes you'll see a 0 from the left, sometimes you'll just see a 0 for shorthand. So we want to consider that unit step function, and we want to Laplace transform that. So we're going to take that function given by t, and to signify a Laplace transform, we have an L with these squiggly brackets here, and then our function of t inside the squiggly brackets, and that represents this integral transform that we're doing. So if we look at this function, we know that the unit step function won't start until just after 0, and after t equals 0, this unit step function is a 1. So we can replace this integral with this integral on the right here. So from that, we just integrate this as we normally would to get that it is equal to 1 over s. So we can say that the unit step function transforms to 1 over s. Now we can look at a constant function, just a, which doesn't vary with time, and pull that out of the integral, and we're simply left with what we had up here. So we can say that a transforms to a over s. Now we can look at another function. We're going to look at a few functions just to have a rough outline of how we can do these integrals, and then I'll give the full table. So if we look at a function t, our Laplace transform integral becomes this here. We use integration by parts to break up that integral to have this term here on the right, and we can evaluate that such that t transforms to 1 over s squared. So moving on to the next function where we have a little bit more complexity, we're going to look at cosine omega t. So we set up that integral. We have our integration by parts. We can evaluate this left-hand component, keep track of that for later. Then on this right-hand side of the component, we use integration by parts again. So doing that, we simply break up this integral into two parts. So if we look at this left-hand side, we have this cosine term being transformed. If we look at the right-hand side, this last term also has everything that's in that integral, plus these constants. So we're going to move this term here to the left-hand side, and then we can factor things out to get this expression here. Notice this integral evaluated to 0, and we've got a lot of arrows all over the place, but this is a messy problem, so the math gets a little bit messy. But the equation that we are then looking at, simply given right here. And from this, we don't actually have to evaluate this integral. We can simply divide by this 1 plus omega divided by s squared. Simply have that this integral is equal to this, where this integral is also equal to the Laplace transform of cosine omega t. That's the trick that we do. So then we can multiply by s squared on the numerator and denominator. Simply get that the Laplace transform of omega t is equal to s divided by s squared plus omega squared. And lastly, we just want to consider our derivative function. So let's plug that in, see what it does. Well, if we plug that in and then try integration by parts, we can set u equal to e to the minus st, and we can set dv equal to d dt. A little bit odd. But then we get into some confusion about what is equal to v. How do we do this integration by parts? And yes, there are ways to do it and there are shortcuts, but the method we're going to look at is let's use a test function g of t. So to do that, we get this integral right here. Or now we can set dv equal to the time derivative of g of t. We can do our integration by parts and simply arrive at the Laplace transform of this function is equal to this first term with the integral of the second term. So from this integral term, we can see that inside the integral, that's just going to be equal to the transform of g of t. And we can evaluate this first term with the limits, and we can arrive that the Laplace transform of the derivative of g of t is equal to this expression here. This is where things maybe get a little bit abstract, and we're going to assume that g of t doesn't explode as t goes to infinity. So it's a realistic bounded function per se. So that being said, at the case of t going to infinity, we know this exponential is going to blow up, but if this g of t doesn't blow up, this term goes to 0. And if that's the case, we can say that the Laplace transform of a derivative of some function is equal to s times the Laplace transform of that function minus g at 0, or 0 from the left, in the time domain. So here's most of the Laplace transforms and properties that we are going to deal with. But if we have an RLC circuit like we had before, we know that the differential equation in the time domain will look like this. But in the Laplace transform domain, or the complex frequency domain, our equation is going to look something like this. Not exactly, because we will have some zero state conditions. But what this really does is it turns a differential equation in the time domain into an algebraic equation in the complex frequency domain. So this has some similarities to phasors and how those helped us, and we'll see how we can analyze circuits in the next videos.